Let's look at section 4.4, division of polynomials. The building block of polynomial division is dividing a polynomial by a monomial. To do this, divide each term of the polynomial by the monomial and simplify the quotients using the rules for exponents. So let's look at this division problem. Alright, so we want to divide 4x to the fourth by 4x squared. We want to divide negative 16x cubed by 4x squared, negative 32x by 4x squared, and positive 10 by 4x squared to divide this polynomial by 4x squared. So it really means to divide each term by 4x squared. So the rules of exponents say that 4 divided by 4 is 1, x to the fourth divided by x squared is x to the 4 minus 2. 16 divided by 4 is 4. X cubed divided by x squared is x to the 3 minus 2. Negative 32 divided by 4 is negative 8. X divided by x squared is x to the 1 minus 2. Now 10 is not evenly divisible by 4. But I do notice both 10 and 4 are evenly divisible by 2. So 10 divided by 2 is 5, 4 divided by 2 is 2, and x squared will remain in the denominator. So let's simplify this. The first term in this division is x squared, the second is negative 4x, the third is negative 8x to the minus 1, and the fourth is 5 over 2x squared. Now I don't want negative exponents in my final answer, so I'm going to write 8x to the negative 1 times 8 over x. And notice that would satisfy a simplified final answer. No negative exponents, no zero exponents, no base appearing twice in any of the terms. Now one thing to keep in mind here is that when we did 32x over 4x squared, if we divide 32 by 4 to get 8, but if we realize that the largest exponent on x was in the denominator and know that that means that that term is going to remain in the denominator in our final answer, we could have brought the exponent of 1 on x in the numerator to the denominator by changing its sign. So the denominator is really x to the 2 minus 1, which is x to the first power in the denominator. We'll look at this again when we look at the final problem on our worksheet. So long division is what we want to look at next. We're dividing polynomials using long division. We're going to divide the first term of the dividend by the first term of the divisor. We're going to multiply the result of the division by the divisor and write this result under the dividend, making sure to line up like terms. We're going to subtract the result of the multiplication from the first two terms of the dividend. This should really just say first terms of the dividend. Depends on how many terms are in your divisor. Then we're going to drop down the next term and repeat the process. So let's take a look at doing this for the first problem in our worksheet. We actually want to do this by long division, write our final answer on the line, and then we want to use synthetic division to do the division problem and compare our results. So first let's just do the long division, and then we'll talk about synthetic division. So here's what I write for long division. This is the format in which I write long division. And I'm going to divide x into 3x cubed. The result is 3x squared. I'm going to put that in the quotient. So x into 3x cubed is 3x squared. So that's going to be my first term that I write in the quotient. And now I'm going to multiply 3x squared by both terms in the divisor. 3x squared times x is 3x cubed. 3x squared times negative 3 is negative 9x squared. Now it's important to note that I'm actually subtracting here. I can always, however, change my subtraction to an addition as long as I change the sign of what I was subtracting to its opposite. So both terms get changed to the opposite. 3x cubed becomes negative 3x cubed. Negative 9x squared becomes positive 9x squared. The first addition should always be 0. The second probably won't be, could be, but probably won't be. And in this case it's 2x squared, and I bring down the next term. And I repeat this process. So x into 2x squared gives me positive 2x. Every term in the quotient that's not the first term of the quotient has to have an operation sign in front of it. 2x times x is 2x squared. 2x times negative 3 is negative 6x. And I subtract. Remember that first subtraction, if I change it to an addition, then it would be the first addition, should always be 0. And then negative 5x plus 6x is simply x. And I bring down the positive 11. So now I want to divide x minus 3 into x plus 11. And notice I need to keep dividing until my subtraction yields something that has a degree less than the divisor. In this case, the divisor has degree 1. So when I add 11 to positive 3 and get 14, that 14 has degree 0. My divisor has degree 1. So the division is finished. So when I write the answer, I write the quotient plus the remainder, which is 14, over my divisor, which was x minus 3. Let's take a minute and let's talk about synthetic division. Here you're dividing polynomials using a shortcut method, and you use this instead of long division. So as long as you're dividing by a binomial of the form x minus c, you can use this process. You use zeros as placeholders for missing powers. You line up like terms. You work only with coefficients because the position of the coefficient will determine the power of the term. So this only works for a certain type of division problem. And our divisor, x minus 3, is of the form x minus c. And so I can use synthetic division in this case. So my c is 3. C is what you're subtracting from x in the divisor. My coefficients of my dividend are 3, negative 7, negative 5, and 11. Notice how those are merely the coefficients of my dividend. I'm going to draw a line, leaving space between that first row. And I bring down the first term, multiply it by my c, get 9, add, repeat the process. 3 times 2 is 6. And notice how that 2 in my synthetic division, the 9 is the 9x squared in my long division. It's the 9 of the 9x squared. The 2 is the 2x squared under the 9x squared. The 6 is the 6x under the negative 5x in the long division. And I keep repeating this process. And I notice that this 14 is my remainder. So in synthetic division, the last number is always your remainder. It'll always be a number. And notice that the numbers in front of the remainder are the coefficients of my quotient. So the 3, the 2, and the 1 are the coefficients of the quotient, 3x squared plus 2x plus 1. So we see that we're able to use a shortcut in this special case where my divisor can be written as x minus c. Alright, let's look at this next problem where we want to divide x plus 2 into my polynomial, x to the 4th. And the first thing I'm going to do is I want to look at x plus 2 as x minus c. So that's x minus negative 2. Alright, and I'll need that for my my synthetic division. I don't need it for my long division. So my dividend is x to the 4th plus x cubed minus 1. Notice how I fill in the missing x squared and the missing x power with 0x squared and 0x. So x goes into x to the 4th, x cubed times, multiply x cubed times x plus 2 and subtract. Then I can change it to an addition as long as I change the signs of what I was subtracting to their opposites. And now I'm adding. So x cubed plus a negative x cubed is negative x squared. Negative x cubed, I'm sorry. And I'm going to bring down the 0x squared, and I'm going to divide x into negative x cubed, and I get negative x squared. Negative x squared times x is negative x cubed. Negative x squared times 2 is negative 2x squared. And let's change that to an addition legally by also changing the signs of what I was subtracting. And my difference, or my sum, I can look at it either way, is 2x squared, and I bring down the 0x. X into 2x squared is positive 2x. 2x times x is 2x squared. 2x times positive 2 is positive 4x. And I want to subtract. Let's change that to an addition and change the signs of what I was subtracting to their opposites. So 0x plus negative 4x gives me negative 4x. And I bring down the minus 1. Notice I need to keep subtracting until I need to keep following the process until my subtraction yields something that has a degree less than the degree of my divisor. And notice x divides into negative 4x negative 4 times. So my result is my quotient plus my remainder over my divisor. And let's use synthetic division. Here we need to look at x plus 2 as x minus negative 2, and we recognize that our c is negative 2. Our coefficients are 1, 1, 0, 0, negative 1. Notice how I must fill in missing terms with zeros. Bring down the 1, negative 2 times 1 is negative 2, plus 1 is negative 1, negative 2 times negative 1 is 2, plus 0 is 2, 2 times negative 2 is negative 4, plus 0 is negative 4, negative 4 times negative 2 is 8, 8 plus negative 1 is 7. So notice how these first three numbers are the coefficients of my quotient, The last number is my remainder. So this shows me the comparison. Notice how the synthetic division is certainly sleeker and simpler if it is eligible for use. And notice I can only use it when my divisor is of the form x minus c. So it's a great method because anything that saves you time but preserves your ability to do things correctly is helpful. Alright, so we see the comparison and notice in both cases the final answer is the same. Now here I have to use long division because my divisor x squared plus 2 is not of the form x minus c and can't be written in that form. So I can't use synthetic division here. Notice I'm missing an x term, so I'm going to write that as 0x. So if there are missing terms in my divisor, I fill those in. And if there are missing terms in my dividend, I fill those in. So I fill in 0x squared and 0x for the missing x squared and x term. X squared goes into x to the fourth, x squared times x to the fourth is x squared times x squared is x to the fourth. X squared times 0x is 0x cubed. X squared times 2 is positive 2x squared. And I'm just going to do subtraction. I'm not going to change my subtractions to addition in this problem. But notice how you have to be very careful. 0x squared minus 2x squared is negative 2x squared. And I'm going to bring down this 0x. X squared into x cubed is positive x. X times x squared is x cubed. X times 0x is 0x squared. X times 2 is positive 2x. And I subtract. Negative 2x squared minus 0x squared is negative 2x squared. 0x minus 2x is negative 2x. And I bring down negative 1. X squared into negative 2x squared is negative 2. Negative 2 times x squared is negative 2x squared. Negative 2 times 0x is 0x. Negative 2 times positive 2 is negative 4, and I subtract. So negative 2x minus 0x is negative 2x. Negative 1 minus negative 4 is positive 3. And notice the division is finished because the remainder is degree 1 and my divisor was degree 2. So the degree of my remainder is smaller than the degree of my divisor, so the division is finished, and the division is the quotient plus the remainder over the divisor. And I write the divisor in its most concise form. I don't put the 0 filler term into the final answer. Okay, so x squared plus x minus 2 plus negative 2x plus 3 over x squared plus 2 is my answer. Or if I wanted to write the subtraction of the remainder over the divisor, notice how I have to not only change the sign of the 2x, but also have to change plus 3 to a minus 3. So a lot of people make a mistake. It's best to just write it as plus the remainder over the divisor. If you do want to write it as subtraction, you have to do so correctly. So notice the correct form if you write this as a subtraction. Alright, we have a theorem we need to look at called the remainder theorem. If a polynomial f of x is divided by x minus c, then the remainder is f of c. And let's look at where this comes from. In general, f of x divided by divisor d of x will equal f of x over d of x, which will equal my quotient plus my remainder r of x over my divisor, d of x. For any f of x, d of x, r of x, and q of x, which are polynomials for which the above is true, and by above I mean what I'm drawing this box around, then if I multiply, so notice how in this particular case my remainder was negative 2x plus 3. I knew that was my remainder because its degree was smaller than the degree of my divisor, which was 2. So notice that the degree of your remainder will always be less than the degree of your divisor. That's true always. So if f of x over d of x is equal to the quotient plus the remainder over the divisor, then when I multiply by d of x on both sides of the equation, every term gets multiplied by d of x. And notice d of x can't be 0 because I can't divide by 0. And so this turns into f of x. Okay, so f of x, when I do this product, f of x is q of x times d of x plus r of x. So that's true in general, no matter what type of polynomial I'm dividing by. If I'm dividing a polynomial by a polynomial, f of x will equal the quotient polynomial q of x times the divisor polynomial d of x plus the remainder polynomial r of x. Now if d of x is of the form x minus c, then notice that the degree of x minus c is 1. R of x will simply be, the remainder will simply be a constant. Its degree has to be less than the degree of the divisor. So if the divisor degree is 1, the remainder degree has to be 0. So it's a constant. So in the case where the divisor is x minus c, f of x is q of x times x minus c plus r. R is just a constant. It doesn't depend on x. So f of c then will be q of c times c minus c plus r. But c minus c is 0. So f of c equals q of c times 0 plus r. Anything times 0 is 0. So this is just 0 plus r, or r. So f of c is my remainder. And that's why the remainder theorem is true. So this is just explaining, if you were wondering, why is this theorem true? This is why. So we want to use the remainder theorem to determine the remainder of the division problem, where I'm dividing by x plus 5. So first of all, I want to remember what the remainder theorem is. It says if a polynomial f of x is divided by x minus c, then the remainder is f of c. So the divisor is x plus 5, but I want to write that as x minus negative 5. So my c is negative 5. And it's important to note that my f of x is my x squared plus 2x minus 1. So I'm squaring negative 5, I'm adding 2 times negative 5 minus 1, and that the remainder theorem tells me that's my remainder. So that winds up giving me 14. So the remainder is 14. And here's how I actually use the remainder theorem to show that. It would be incorrect, since you were told to use the remainder theorem, to actually do the division to get the remainder. You want to use the information in the remainder theorem. Another theorem is the factor theorem. So this theorem is for a polynomial function f of x. If f of c is 0, then x minus c is a factor of f of x. If x minus c is a factor of f of x, then f of c is 0. So f of x, remember, is q of x times the divisor d of x plus r of x. Q of x is the quotient. R of x is the remainder. So if d of x is equal to x minus c, then f of x is q of x times x minus c plus r, because remember, if the divisor is x minus c, the remainder is a constant. So if the remainder is 0, that means f of c is the remainder by the remainder theorem. And if that's 0, then r is 0. So if f of c is 0, r is 0, and f of x is just q of x times x minus c. So obviously x minus c is a factor of f of x, because we're multiplying x minus c by q of x to get f of x. To be a factor means you can be multiplied by something to give f of x. So let's use the factor theorem to determine if x minus 2 is a factor of this polynomial. So x minus c is x minus 2, so c is 2. So f of c is f of 2, and f of x is this polynomial, x to the 4th. So I raise 2, so f of 2 is 2 to the 4th plus 2q minus 8 times 2 minus 8. So f of x is x to the 4th plus xq minus 8x minus 8. And notice that this result is 0. So f of 2 is 0. So the factor theorem tells me x minus 2 is a factor of f of x. Our final example is number 6, where we're dividing a polynomial by a monomial. And I just want to, we looked at this before we started the worksheet. We want to take 3x cubed minus 27x squared minus 15x plus 11 and divide it by 3x squared. Notice how we have to parenthesize the polynomial we're dividing into to write this correctly with the division symbol. Or we could write it as a fraction with the polynomial in the numerator and the divisor in the denominator. But ultimately, every term of that numerator is going to get divided by that divisor, 3x squared. And remember that simplifying means there are no zero and negative exponents. And all fractional expressions are simplified. So negative 27 over 3 is a negative 9. X squared divided by x squared is x to the 2 minus 2. When I do this third division, I can think of this as negative 15 over 3, which is negative 5. x to the first is in the numerator, x squared is in the denominator. So I'm going to bring the smaller exponent to the larger one, and that turns into a negative 1 in the denominator. So this, I don't want to have 0 or negative exponents in my final answer. Remember that x to the 0 is 1. So this is x minus 9 minus 5 over x plus 11 over 3x squared. That's my final answer.